Hello everyone, my name is Anup P. Pushkar. I welcome you all to this new series on solutions to GATE chemical engineering questions. We'll be starting this series with chemical reaction engineering questions from previous years. In part 1 of this series, we'll be looking at the one-marker questions from GATE 2024. So let's begin with the first question. The question says, the ratio of activation energy of a chemical reaction to the universal gas constant is 1000 Kelvin. The temperature dependence of the rate constant follows the collision theory. Find the ratio of rate constant at 600 Kelvin to that of 400 Kelvin. So first let us note down the given parameters. So we have the ratio of activation energy to universal gas constant EA by R is equal to 1000 Kelvin. And we are given two temperatures of interest, 600 Kelvin and 400 Kelvin. So given the validity of collision theory, we need to find the ratio of rate constants. So let's look into the solution. So since the reaction obeys collision theory, we can write that rate constant is directly proportional to temperature per half into exponential of minus E by RT. Now expand this definition to the given scenarios, we get K1 by K2 is equal to T1 by T2 power half into exponential of minus 1000 by T1 divided by exponential of minus 1000 by T2. On substituting the temperature values, we get ratio of rate constants as 2.818. So hence the solution to this question is option A, 2.818. So let's move on to the second question. The rate of reaction A giving B is 0.2 moles per meter cube second for a particular concentration Ca1. The rate constant of the reaction at a given temperature is 0.1 meter cube per mole second. If the reaction concentration is increased to 10 Ca1 at the same temperature, what is the reaction rate? So we have been given the rate and concentration terms for a particular case, which is 0.2 and Ca1, and given rate constant as 0.1, what will be the rate and what will be the rate for a concentration of 10 Ca1? So if we observe the units of rates and rate and rate constant, it is evident that the reaction is second order in nature. So hence we can write the rate expression as Kca square. Now expanding this expression for the two cases and taking the ratios of the rates, we get R1 by R2 is equal to Kca1 square divided by Kca2 square. So after cancelling out K and substituting the values of R1, Ca1 and Ca2, we get R2 as 20 moles per meter cube second. So hence option A, 20 is the right answer. Let's move on to the next question. Two parallel first order liquid phase reactions, A giving B and A giving C, are carried out in a well mixed isothermal batch reactor. The initial concentration of A in the reactor is 1 kmol per meter cube, while that of B and C is 0. After 2 hours, the concentration of A reduces to half its initial value, while the concentration of B becomes twice that of C. What are the rate constants? So here is the representation of the given parallel reaction, A giving B and C. So the reaction is carried out in a batch reactor and the inlet consists of only A. The concentration of A at the inlet is 1 kmol per meter cube. After 2 hours, it is given that Ca is equal to 0.5 kmol per meter cube, while Cb is equal to 2 Cc. Hence, we need to find the rate constants. First, let us consider the mole balance of A. We can write minus dCi by dt as K1 plus K2 times Ca. So we can rearrange this expression and we can integrate both sides of the expression. On the LHS, we can integrate from Ca0 to Ca, whereas on the RHS, we can integrate dt from 0 to 2. So on simplifying, we get ln Ca0 by Ca is equal to 2 times of K1 plus K2. On substituting the values of Ca0 and Ca, we get K1 plus K2 as 0.35. Now, by observing the values of K1 and K2 given in the problem, we can infer that the values of K1 and K2 of 0.23 and 0.12 satisfies the given equation, equation 1. So hence the correct option to this question is option B. So without explicitly finding the values of K1 and K2, and by observation, one can figure out the values of K1 and K2 for this question. However, for explicit solution, one can look at the ratio of rates of formation of B and C, which is basically dCB by dt divided by dCC by dt, which is equal to K1 CA by K2 CA. So we can cancel out dt on the LHS and CA on the RHS, we get K1 by K2. Now expanding dCB and dCC, we get CB minus CB naught in the numerator, and in the denominator we get CC minus CC naught. Given CB naught and CC naught are 0, hence we get CP by CC is equal to K1 by K2. It is given that CP will be equal to 2 CC after 2 hours. So hence we get K1 is equal to 2 K2. Now using this equation along with the equation 1, we get the values of K1 and K2 as 0.23 and 0.12 errors. So hence this agrees with the values given in the option B. So with this we come to the end of the first part of this series. If you like this video, please share and subscribe to this channel, and stay tuned for part 2, which consists of 2 marker questions from GATE 2024 related to chemical reaction engineering. Thank you.